minute, madam will introduce you and then we can start, sir.
Yes, yes. Fine.
Madam.
Yes, sir.
Okay.
Okay. Good morning, everyone. Welcome back to the STTP entitled Mixer Signal Design Day 5 morning session. Today's speaker, Dr. Rohit Lorenzo Garu. Welcome back, you sir, to the another session. Already we had a session with the same speaker on low power VLSI design. Today he is here with a new topic, dynamic CMOS design. Now I request Dr. Rohit Lorenzo Garu to take over the session.
Okay. Good morning, all. So, day before yesterday, I have taken the topic of low power VLSI design. So, I will continue some portion in that because some portion is left. And if the time allows, I will go for dynamic CMOS logics. Okay. So, my screen is visible to all?
Yes, sir.
Okay.
Sir, put in a presentation mode, sir. It is visible.
Yes, yes. I just going to that slide.
Okay, okay.
Yes. So in previous class, in previous lecture, I have covered up to here. Like we have studied different types of power dissipation and power dissipation at various abstraction level. Okay. So we have just understood what are the enemies and why it happens. What are the sources of power dissipation? Okay. Now in this lecture, we'll see what are the solution. Okay, what are the solution for power dissipation? So the first I will start with design technique to reduce switching activity. Means if the transition is more, like 0 to 1, 1 to 0, if the transition is more, then the power dissipation will be more. Okay, so how we can reduce the switching activity, that all we'll see. So like in the figure you can see there is a chain structure and tree structure. Okay, now if you see there is a one path from A to F, A B to F, and one path will be from this to this. So if you see the delay in this path, because three gates are arranged in the series. Okay, so the delay in this case will be more. But you can see the second structure, it is a balanced path. So delay in this structure is less. Okay, so suppose you can see if I give some signal at here, so it will reach to O1 and another signal will reach to O1, but they will reach at same time, because this gate also have finite delay, this gate also have finite delay, but all are equal. But if you see here, this gate will take some time, this gate will take some time, and here the delay will be more because the two gates are involved. So if I see the power dissipation, in which case the power dissipation will be more. So it's obvious the delay is more in this. So power dissipation, you can say the glitching power dissipation. So in the previous class we have discussed the glitching power dissipation. So glitching activity will be more in this case. Okay, so glitching power dissipation will be more in this case, but less in this case because of tree structure. So what we understood from this, if by see this and this gate will give the same functionality. There is no change in the functionality. Final output, if you check for both the chain structure and tree structure, the same. Only just we have done the rearrangement. Okay, so by logic restructuring, you can minimize the power dissipation. Okay, I hope this is clear to all. Now, another thing that input ordering. Okay. So by input reordering, we can also minimize the switching activity. How we can do? So if we see here in the right hand side, you can see there is PA, PB, PC. The different switching probabilities are given. Okay, different switching probabilities are given, and if we just change the input order, simply we can minimize the switching activity. How we can minimize? So this is the probability is given at A, PB is given here, PC is equal to given here, that is a 0.5, 0.2, 0.1. So PA is equal to suppose 0.5, okay, PB is equal to 0.2, okay, and PC is equal to 0.1. Okay, so in first case, if I want to, what is the probability here, what is the switching activity here? Simply if you multiply 0.5 into 0.2, it will come 0.1, and 0.1 simply you will get here 0.9. So what is the activity here? 0.09. Okay. Similarly, if I multiply this 0.09, 0.1, so it will come here 0.009. Okay, and simply you have to multiply 0.009 and 1 minus 0.009. So the total activity like 0.009, it means 1 minus 0.009. Okay, now here, now we'll see this case. PB is equal to here 0.2 and PC is equal to 0.1. Okay, so simply if we calculate the switching activity here at this node, 0.02 and 0.98 and simply 0.016. So actually what I want to convey from this, if you see at this end, switching activity, the switching activity less. Here. So switching activity at this end is less, and for this a same circuit is more. Just if you see, I have just reordered the pin. Here is AB. Now here you can see the BC. Okay, here is BC. Just I have changed. Okay, and because of there is a less switching activity, and overall it will. So what I actually want to do here, the higher probability inputs switch at the later stage. Okay, higher probability inputs are switched at the later stage is to reduce the switching activity. So if you can see here 0.5, 0.2, 0.1, here is A, and I shifted this A in second case here. So among this, if you can see the switching activity of this PA is higher. So I shifted at this to the later stage. Okay, so if you shift it at the later stage, you can be able to minimize the switching activity, and you also able to minimize the power dissipation. This is the logic. Okay. Now, another technique we can minimize the switching activity is that like we have transmissions. One is parallel, another one is serial. So you can see from this figure, if it is in the parallel, there are two capacitors are attached here. Okay. So time multiplexing on single hardware. So or here you can see we use multiplexer and demux. So at the source end there is a mux, at the receiving end there is a demux. So you can say in the parallel transmission there is a two capacitor is associated here, and here is only one capacitor. So when the data will transfer, these two capacitor will charge and discharge, charge and discharge, and because of this transition will happen. Okay, and again here only the one capacitor will charge and discharge. So switching activity in this case will be more. So as we know the formula, that's a P dynamic alpha CV square F. Okay, so transition in this case will be more. So you can see the power dissipation in parallel transmission is more as compared to the serial data transmission. Okay, so we are not see overall objective that whenever like we are doing the pin reordering or logic restructuring or multiplexing, our functionality should. Okay, but we are designed in such a way that we are able to minimize the power dissipation, and same time we need the same functionality. Our functionality should not disturb. Okay. Now another technique in minimizing power dissipation, like bus encoding. There are several techniques are available. So I will discuss under one technique, that is a gray coding under bus encoding. Okay, so you can see here what is in bus encoding. A considerable amount of power is dissipated from transmission of data over input and output pins. So you can say there is, and here is a receiver chip, and we are sending whenever sending the data, we are encoding the data, at the receiver end will decode. Okay, so it is possible to save significant amount of power, reducing the number of transition and the switching activity as the process input output interface. Okay, so the technique is like if I want to reduce the switching activity, that is a bus encode. We have to encode the data. So there is a different way we can encode the data. Okay, so by encoding the data, you can minimize switching activity. How we can? So I will discuss only one example here. That is a gray coding concept. So all of you know this gray coding concept. Here you can see there is a binary code and it is gray code. Okay. Now one thing you notice here, if I encode at the sender and if I encode my binary code into gray code, the switching activity transition will reduce. How? So at this end, if you see how many transitions are there, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1 again. So again you can say there is multiple transition if I count here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, around 15. And here 1, 2, 3, and 1, 2, 0, this. And yes, so overall I count 1, 2, 3, 4, 5, 6, 7, 8. So you can see the transitions are reduced here. Here in this case it is 15, but here in this case it is reduced to 8. Similarly, you can check for other. So if you compare this line and this, you can check. Okay. So what I want to say, if I encode my data and I will send in this form, so overall transition will reduce. And by reducing the transition, I am able to reduce the switching activity. So in this way, I can minimize power dissipation. So this is one technique. In bus encoding, there are several techniques out there. Okay, so I cannot discuss. It's not possible to discuss all because it will consume more than one lecture if I start discussing bus encoding. So in brief, I discuss one technique. Okay, now another technique to minimize the power is the supply voltage scaling. Okay, so as we know in dynamic power dissipation, that is alpha F CV square F, and VDD static power dissipation is VDD into I leakage. Okay, so in both the case, if you notice, dissipation is directly related to the directly proportional to the supply voltage VDD. Okay, so if I minimize this factor VDD, if I reduce or scale this supply voltage VDD, so simply I can minimize the power dissipation, whether it is a dynamic or static. Okay. My voice is clearly reaching. There is any lag or something anybody is facing?
No, sir. No, sir. It's in sync.
Okay, thank you. Okay. So here you can see, sir. See, I am there is a I can minimize the VDD supply voltage, but certain limit. Okay, if we go beyond that limit, there is another issue will come into the picture. And VLSI there is a off. Okay, so what are the problems will arise? So see here, you can see the energy here. So this factor at reduced supply voltages, see it is less. As we goes on increasing the supply voltage, it start rising. Okay, so the power that is related to your energy, so it means power dissipation also goes on increasing as you goes on increasing the VDD supply voltage. Now, what will happen to the delay? See, if I reduce the supply voltage, my delay will be more. So at reduced supply voltage, my delay will increase. As I goes on increasing the supply voltage, my delay will reduce. So there is a trade-off in the power dissipation or supply voltage. Okay. So how? See, power is directly, you can see there is a direct relation that is VDD and P. Okay. Now here you can see the delay. There is an inverse relation. Finally, if you check here, it is inversely proportional to the VDD. Okay. So if I increase VDD, the delay will reduce. If I reduce the supply voltage, the delay will increase. Okay. So there will be a performance reduction in supply voltage. Okay. So I need a one technique or there is suitable mechanism, like I need devise a suitable mechanism to contain these losses in performance due to supply voltages scaling and for realization of low power high performance circuit. Because as a good for good VLSI chip, I want low power and low delay. Both the things I want. Low delay means high performance circuit. So both the things I need. So I need a one suitable mechanism to achieve both the things. Okay. Okay. World-scaling approaches. Several approaches are there. Scale down the supply voltages like static voltage scaling, multi-level voltage scaling, dynamic voltage and frequency scaling, adaptive voltage scaling. So first one is the static voltage scaling. So in this case, the fixed supply. So what is the static? In this case, the fixed supply voltage are applied to one or more subsystem or blocks. So means I am just like you can say scale down and one supply voltage, and I am fixed to that. Okay. Now multi-level voltage scaling. This is extension of SVS where two or few fixed discrete voltages are applied to different means. We'll see in the board. Okay, so multiple multiple scaling. What is that? Suppose there is a chip. Suppose this is a chip, and there are several blocks are there inside chips, and applying like VDD1 and VDD2, VDD3. So, we are supplying supply voltages. Like suppose this is a 5 volt, and suppose this is 4 volt and 3 volt. Okay, so you can say there is a multiple availability of the supply voltages in multiple voltage scaling. Okay. Now another technique, that is dynamic voltage and frequency scaling. Okay, so this is MVS, where a large number of discrete voltages are applied in response to changing the workload conditions on system. So depending upon the workload, what we the different supplies we are using. Like suppose if any block is there, like this is a chip, and suppose there is a load something. So depending upon the the workload is also changing. Okay. So based on the workload, the supply voltages will scale. So if the workload is more, so it will demands more supply voltages. So then and the chip will tune to the higher supply voltages. If the workload load is less, it will tune to the lower supply voltages. So this is in dynamic voltages and frequency scaling. Now adaptive voltage scaling, this extension of DVBS, where is a closed loop control system continuously monitor the workload and adjust the supply voltage. So it's a feedback type of system. So by checking the workload, it will feed back to the chip the information that this much is workload. Now you will supply. Now you have to supply this much amount of voltages. So it's a control system type of thing. Okay. So I will just discuss this static voltage scaling one technique. Okay. Okay. So static voltage scaling, here is device feature size scaling and architecture level approaches. Okay. So device level, how we can minimize, and architecture level, how we can minimize. Okay. So device feature scaling, already I think you may be knowing the scaling of the MOSFET transistor. Okay, so scaling is nothing, just it is concerned with systematic reduction of overall systematic reduction of overall dimension of the devices. Okay, and as allowed by suitable available technology while preserving the geometric ratios found in the larger devices. Okay, so just reduction of sizes. So that there is a device size scaling in this. If you see, there is a earlier 1985 250 nanometer, then once, and I have up to the 2009, it will reach to 2009 45 nanometer. Okay, So if the device dimension is scaled down, automatically we need to scale down other parameters. Okay. So what are other parameters? You can see this is a MOSFET structure. This is a gate, source, drain. You can see the one number, that is oxide. The oxide, if the device dimension is scaled down, the based on the technology, we are scaled down TOX by S. So S is defined as a scaling factor. So it depends upon the what type of technology you use, 45 nanometer, 32 nanometer. The scaling factor is related to that. It will be uh, set according to the technology. So oxide thickness is TOX by S is will scale down. Now you can see the doping concentration. We are multiplying here. Why we multiplying here? Because we have to maintain the electric field, proper electric field. So that purpose we need. Okay. And length, you can say the 3 number, this length is also scaled down by S. X depletion, that is a fourth, that is the junction depth. Okay, junction depth, that is also xj by S. Width is W by S, and Na is Na by S. So we'll see there is a two type of scaling. There is a two type of scaling are there. One is constant field scaling and another one is constant voltage scaling. So this is your actually the constant field scaling. Sorry, I not written here. Yes, so this is your constant field scaling, or you can say it is a full scaling. Okay, so in order to maintain the electric field, because name itself is a constant field, uh, electric fields, charge densities must be increased by a factor of S. So these are the conditions for the constant field scaling. So length will scale down as L by S, W is scaled down by after before scaling it is W, after scaling it is W by S. Thickness, junction depth, VDD, supply voltages we are scaling. See, we are studying under supply voltage scaling. So VDD is also scaled down. Threshold voltage is also scaled down, and Na and Nd it will be multiplied. Okay, so we have to increase the charge density to maintain the electric field. Now, what will happen to the equations? So if you see the gate oxide capacitance per unit area, it will be changed to S into COX. So it will change, and the equation for like linear region, this is Kn by 2 VGS minus VT VDS square. So if you scale down, the overall will come IDS by S. The current will reduce by a factor of S. Now similarly, before scaling, you can see overall the oxide capacitance S into COX, your drain current will scale by X S, and power dissipation simply it is into V into I. So V into I, so that is V is also scaled by V by S and I is also scaled by I by S. So overall P by S square, and the power density is a power by area. Okay, so you can see here there is a reduction in the power dissipation because it is there is a power is also scaled down. Okay, overall result is that by constant field scaling you are able to minimize the power dissipation. Okay, now there is a another scaling method is a constant voltage scaling. So overall what is this, why we go for this constant voltage scaling? Actually if you see in the chip, there is some certain voltage levels are required, certain part of the circuit, like if there is a chip, so some block needs more voltage. Okay, so sometimes what happen, if I want to boost up, then I need a level shifter type of things to boost up the appropriate voltage equal to another block of the chip. chip. Okay. So at that time, mm, that constant field scaling is not very useful because overall we scale down the supply voltages. I need some constant supply at the some part. So that's why there is a need come for the constant voltage scaling. So overall thing is the same. Voltage is fixed here. Rest of the change will scale. So what are the result for that? The capacitance you can see before scaling Cg and it is Cg by S. The drain current you can see Id and it is changed to Id into S. And the power dissipation P into S and power. So you can see here what will happen here, the power will not scale down. There will be increment in the power dissipation. Okay, so it is preferred sometimes over constant field scaling. But what are the drawbacks in this constant? Like large increase in the current and power densities, okay, may cause serious reliability problem such as electromigration, hot carrier degradation, oxide breakdown, stress. So all this problem will because there is increment. So if the power point of view, like if you want to minimize for low power application, constant voltage scaling will not prefer. Okay. Now another technique in this, that is a parallelism and pipelining. Two techniques are there, and with the help of these techniques, we are able to minimize the power dissipation. Okay, so we'll see. So how we can minimize it? So parallel processing can be an important power consumption in CMOS. Key approach is to trade area for power while maintaining the same throughput. Okay, so we know that supply voltage scaling is the most effective way to reduce power consumption. Unfortunately, the saving in power come at the expense of performance. So all we know, like if I reduce the reduce the supply voltage, there will be saving in the power, but it is comes at the expense of performance. Means there will be penalty of the delay and performance. Okay, so this loss in performance can be compensated by parallel processing. Okay, so what I am doing in this involves splitting into independent tasks. Like if there is a bigger task is there,
Sir, I have one doubt,
I
sir.
divide into the yes,
Yeah.
please ask.
Yeah. Sir, if supply voltage decreases, the power dissipation decreases, but it leads to a delay in the performance, sir.
Yes, right.
That problem can be overcome by reducing the threshold voltage is possible, na, sir?
Reducing the threshold voltages, yes. See, low VT, if you do, the transistor will be a fast.
Yeah, yes, sir.
Yes. So these are techniques are there. That is a body biasing technique is there.
Okay.
Body biasing. Just I will tell you.
Actually, we go for a VT CMOS and MT CMOS technique in order to reduce the drawback. Yeah.
Yes. I will teach that thing. So see, I understood. Like so, low is fast. Low VT transistor are fast and high VT low in speed. Okay, so there is a body biasing technique is there. We can do like VDD. What we are doing, will supply VSS minus delta V, and this is we can just reverse VDD plus delta V. So what will happen? The transistor will be forward body bias, means the VT will reduce. So in this way we can also do. The technique is exist. Hmm.
Thank you, sir.
Now, suppose there is a block. Mm, okay, suppose let us consider example of two 16-bit register. Okay, 16-bit register, and it is we are providing the input A and B. Okay, if 10 nanosecond is the delay of the critical path of the adder, then the maximum clock frequency will be 100 megahertz. So suppose this is a block and there is a frequency F, and the voltage is V reference. Okay. Now we will apply in this the parallel technique. Okay. So this parallelism will help us. We are minimizing the power dissipation. We are minimizing the power dissipation as well as we are minimizing the delay. We are achieving a good performance. Okay. So this is the need for the good VLSI chip. Okay. Now, how they have done? They have done just duplicate that. You can. Okay. So they have divided into the multiple cores. Core 1, core 2, core 3, core 4. Okay. Now what they have done? They allotted the frequency. Okay. They allotted the frequency. So here you can see the same throughput, the number of operation per unit time can be maintained by parallel architecture. So here adder has been duplicated twice. Okay, duplicated twice, and 1 minute. Okay, actually this figure. Hmm. Okay, this multiple core is okay. 0.2. Okay, multiple core actually come. Actually, what they are doing here. Sorry. See what we will do here. Actually, this is your latch. This one is latch, and here they will divide into two parts. I will tell you how we'll do. The wrong figure came here. 1 minute. Yes. Okay. So actually, what they will do here. This is a 16-bit adder, and they will do here the division. Okay, so like suppose two blocks. Okay, and suppose there will be latch. So two latch will be here, two latch will be here. Okay, so there is some input, there is some input, and there is some input, and here. Okay, I think 8-bit here, and finally it will get the marks, and here sometime here will be some control type is given. Yeah. Actually, the voltages, suppose here is a V reference, so they will reduce to V reference 2. And here the voltage reduced by V reference by 2. Okay, and here the frequency is given like 100 megahertz. So it will operate at 50 megahertz, and this portion will operate at 50 megahertz. Okay, so what will happen here? See, so this block will compute separately the first block, and the another block will compute separately. So if you see the power dissipation in this case, like CV square F alpha, like I'm talking about the first case. So alpha V reference square, and the suppose frequency is 100. So it will come something frequency. But if you see in the second block separately, so this will compute something like P is equal to CV reference by 2 and F also 50. So if you see compare, if you calculate this, the power dissipation in this case will be more. But if you compute separately, because at a one time one will go, so it will compute separately, the power dissipation will reduce in this case. Okay, and because of this parallel processing, this system will also a faster. Okay, so this is there in parallel processing, and actually here is a figure come for multiple core. Okay, so this is also a multiple core system. Okay, I will later I will change it. Okay, so here is also like multiple core system, like there are, like suppose several latches are there and multiple cores are there, and they are operating separately, block wise. So whatever the power dissipation is related to the block, if suppose this block is in the operation, so power dissipation will be there, and this suppose these blocks is not in operation, so power dissipation is due to only one block. Okay, so blocks that are operating, that only the responsible for the power dissipation. So this is a concept in this parallel. We are just duplicating the original architecture into the multiple blocks. That's it. And if we reduce the overall the block size, automatically it requires less supply voltages and less frequency to operate. So simply we are just scaling the voltage and as well as the frequency to minimize the power dissipation. Okay. So yes, so they just checked for, like, if there is a one core, like if there is a number of cores are there. So if you see in the multiple core architecture, if there is a one core, it will take 5 volt of supply, and the result will like total is 15 watt. Now if you divide the number of cores into 2, so just we have to minimize, reduce the frequency into 2, means 100 and 100, and supply voltage is scaled down by 3, and you can see it's reduced. Okay, so you can see if I divide into 8 cores, it's the supply voltage we have to further minimize, and the further there is a reduction in the power dissipation. Okay, so this is the impact of parallelism. Okay, but the problem, if you can see what are the drawbacks is there is a area overhead, because we are increasing the number of blocks, and there is a separate, the wire will increase and the mux circuit will increase, and it also increase the leakage, because the blocks that are is a, like one block that is in operation, that consumes the, you can see the dynamic power, but the other blocks that are in the ideal stage, that will consume the leakage. So two drawbacks are there in this parallelism. Okay, now there is a concept, another concept of pipelining. So this is also like a subtask we are doing in this, and how we can minimize the power in the pipelining. So pipelining is nothing, it's just a implementation technique where multiple tasks are performed in overlapped manner. And when it can be implemented, it can be implemented when a task can be divided into a 2 or subtasks, which can be performed independently. Okay. Now you can see here how we can execute. There are different tasks are there. There is a different tasks are available: T1, T2, T3, T4, T5. So at T1 this is computed, at T2 this will be executed, At T3 this will be executed. At T2 time this. Okay, so now you can see here at common at T4 all 4 tasks are computed. At T5 it is computed here. I will explain with the help of a very simple example, daily life example. Just we'll take one example. Okay, now let us consider undergraduate education. Okay, now consider for your BTech course. Okay, so suppose your batch is one batch is entering at 2010 for this program. Okay, to 2010 to 11, 11 to 12, 12 to 13, and 13 to 14. They will pass out by there. Okay, now suppose suppose there is in the institute there is different branches EC. Okay, now one classroom is only allotted. There is availability of resource, like we have only one classroom for EC branch, we have one classroom for CS. So I have the availability of this. So until one batch is not pass out, we cannot take admission of next batch, because I have resource of one classroom. Okay, the next batch when it will enter, when this is 2014, they will pass out normally in the summer. Then at the 2014 the next batch will come, new admission will come for the BTech, if we consider a particular one branch, and again it will take in 2018, and 2018 the next batch will come, and possibly it will be pass out in this if we have one class or one branch. Okay, now suppose we have more classrooms. Okay, suppose we have 4 years BTech program, and suppose we have 4 classrooms. So one classroom the first year will run, in the second classroom second year batch, third classroom third year batch, and fourth classroom final year batch. So just consider batch 1. This is just your first year, second year, and batch 4. One batch is enter suppose at 2010, another batch is entering at 2011. Means it will 2012, 2010 to 11, 11 to 12, 12 to 13. So this is the first year, second year, third year, and finally. Okay, so I have 4 classroom now available. Okay, so my next batch will come at enter at here, then it will go to here, and finally it will 14, and finally it will pass out in this. So like this they can enter here. So every year I can take admission. So finally if you see here, just I will complete this and the final. So you can see at this here the all are running. Okay, so this is what you can see. It is a type of pipeline structure. It is a type of pipeline structure, but what you can see, we require what you can see the drawback in this case, we require more hardware if we talk about the chip. But if you see in the, if you compare with the, they require more infrastructure, like more number of classes, more hostels. Okay. So advantage is that in this case pipeline manner, every year one batch is pass out. So throughput you can see one batch per year. So overall throughput will increase in this case. Okay. So that is the thing in this case. So in pipelining, realization instead of 16-bit addition, 8-bit addition is performed in each stage, and the critical path delay through 8-bit adder stage is about half. Okay, so just what they have done, the area penalty is much less than parallel implementation, and C pipe here. So the capacitance is just, it will be this time. And substituting, if you substitute all these values, you can say the overall power dissipation is minimized by this. Okay. So in parallelism technique, both there is an increase in the hardware, but they are able to achieve both the things. But I tell you, area is not an issue nowadays. If there is, you are achieving the less delay and less power, and if there is a 15 to 20% of area penalty, then it is not an issue. Why it is not an issue? Because we are now reduce deep nanometer technology. I just in the previous lecture show up to 2019 they have designed the processor with 10 nanometer technology. So already we have reduced the dimension, already we have reduced the area, deep nanometer technology. Okay. So with this penalty, if they are 15 to 20%, we are able to minimize the power, able to minimize the delay, then it is a good VLSI chip.
Sir, what is the minimum reducible technology, sir?
That I discussed up to 2019, that is a 10 nanometer. I have
Yes, sir.
in the previous lecture.
7 nanometer, 5 nanometer,
For,
up to
for see, it's reach up to, for Intel processor up to 2019, it's reach up to 10 nanometer. Okay, so actually slowly they are adapting actually, because various things we need to change. Okay, so
sir, is there any limitation, sir? What is the minimum reducible? We can reduce up to 3 nanometer, 2 nanometer, 1 up to what is the limit, sir? If there is any limit, sir?
We cannot say actually what will be the limit.
Okay.
The industries are going on, they are working on this. Okay,
Okay.
so reducing the device dimension. And I'm telling you earlier there are more number of foundries, and currently there is a 4 foundries that exist in the market. That is TSMC, Samsung, Global Foundries, and one more, I think UMC. And all other foundries are now washed out. They are not in deep nanometer technology. Why it is happening? This is because everything is based upon the law of economics. So it requires lot of cost. So 4 players are existing commercial fabrication. Okay.
Okay, sir. Thank you, sir.
Now see, in the pipelining, see what they have done. So earlier you can see that is a 16-bit adder. This is a 16-bit adder. The same. Now how they transform into the pipeline structure. So see here, in the pipeline they just divided into 8-bit, and like this they have done. And similar way, there is a f reference frequency in all this, they will scale down. So you can see this one. So you can see with VDD scaling, like without VDD scaling, this area of this much, power is this much, and this throughput. So you can notice here the power dissipation is decreased and throughput we got better. So both the things we are achieving this pipelining technique. Okay. Now another technique, we can achieve more advantages by combining both parallelism and pipelining. If we combine both the type of techniques, we can reduce some more power dissipation. Okay, so this much we can achieve. So we'll see what they are doing here. So just they have combined, see, this is the pipeline structure, and again this is in parallel. Okay, so they have just combined both the things, and similar like block wise they will minimize the supply voltages and the frequency. Okay, there is a frequencies, and by just minimizing this scale down block wise the frequencies and supply voltage, we can minimize the power dissipation. Okay. So this is impact of parallelism and this. So area is this, you can see the power is minimized by this if we compare X, and throughput this will get this. So these are the advantages we can achieve if we combine both pipelining and parallelism. I hope this is clear. Now another technique, minimize switch capacitance. How we can minimize the capacitance? Okay, so overall we know that this P is equal to CV square F. If we minimize the capacitance, we can able to minimize the power dissipation. So there are several techniques are there in, if you go for the clock gating, like minimize switch capacitance. So I will discuss only one in this clock gating, minimizing switch capacitance, and this is one of the popular technique. Okay, so by minimizing, yes, so by minimizing we can, there you can see in the circuit this 50% power dissipation is related to the, it is a clock related power. Okay, so a major component of processor power is the clock power. It is a 50% of the total power. Okay, so with this technique we can able to reduce more power dissipation. So one of the most successful and commonly used low power technique is clock gating, and it is based on the observation like large number of transition is unnecessary. Can be suppressed without affecting functionality. So you can see the there is a percentage. Yes. Yes. Anybody want to ask question? Anybody have question?
I have small question, sir.
Yes, please ask.
If you are saying that if the processor power is clock power, something you have said, right?
Yes,
so,
yes.
But thing is that if the power reduces, the speed also reduces, no, sir. Then what is the remedy behind that? How to increase the speed if the
If the power is reduced, like if we talk about like VDD, okay, if we VDD, so if we reduce like the power, the delay will increase. This is your question, no?
no, sir. You are saying that one of the way to decrease the power is some by clock power, by clock signal frequency. You said, no, sir.
Yes, yes, by clock gating.
By clock gating, then obviously delay also decreases, no, sir.
I will tell you, just look some more slides. I will explain how we are doing this. Okay, so once I explain, then you tell me you got your answer or not.
Okay, sir.
Okay, so just we'll come to next slide. So the clock loading, like if you say there is a associated with local clock drivers, sequential cell internal clocks, global clock drivers, and clock loading. So what we are doing actually in this technique, I am simply telling. See, this is actually the power management technique. Suppose there is a chip and there are several blocks. Okay, and there is a clock associated with. There is a clock associated with this different blocks. Now, this is what one kind of it is power management technique. So some blocks are not in use. At the same time, I need, suppose this block is working. Okay, and this block is not working. I don't require so at one time, suppose I don't require the work from this block. I require the work from this block. So what I'm doing, with the help of clock gating, I will disable this block. So this is the clock gating technique. Suppose I don't need the work from one block, I will disable that particular block. I will disable, if I don't require the work from two blocks, I will disable those blocks. Okay. So if I disable those blocks, then it will definitely will not consume the power. The blocks which are in active mode, that will only consume the power. So with the help of clock gating, we are actually disabling the blocks. This is a clock gating technique. So we'll see in detail here. What is this? Suppose this is a clock. Okay, this is the clock and going, and here is that. So when this clock is running, what? There is a dynamic power dissipation. But when the clock is gated, it is disabled, there is only leakage. There is no dynamic power dissipation. Okay. So the mechanism here, the usage of functional element, okay, there will come to it. So clock gating is what? It will shut off the certain portion of the circuit that are not in use. Okay, so dynamically preventing the clock from propagating to some part of the circuit under certain condition. Okay, so what I want to say, we are preventing the clock that are not in use. Some blocks that are not in use, we are preventing the clock in that. So how we can do this? So suppose this is one circuit and there is a one block and there is a clock is attached to that. And now suppose this functional unit is not in use. So this is enable signal. So I will not enable this. I will not enable this. So clock will not go to this because I don't. I don't need the work from this block. So there is no need to provide the clock. It is simply way I can say there is a suppose a AND gate. Okay. If I put En is equal to 0, so whatever the input I will give, it will be 0. So the what is the block is attached to this, it will not take. So there will be no power dissipation. So like this, there is a big circuit. If you imagine, if you bigger block, we can stop clock that are not in use. In this way, we can able to minimize the power dissipation. So your question is clear? Yes. Anybody? You have doubt? All of you understood this clock gating principle? Okay. Yes, one guy is asking the question, your doubt is clear or not? Am I audible?
Clear, sir, clear.
Okay, okay, thank you. Okay, so the next is standby leakage reduction technique. So till now what we have studied, that is our overall focus on minimizing the dynamic part dissipation. Okay. Can we take 5 minutes break, ma'am? Hello? 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 I want to take 5 minutes break. Voice audible to all?
Yes, sir, audible, audible.
I will gather after 5 minutes. Okay.
Okay, sir, proceed,
So
proceed.
time is 11:06. We will come at 11:01. We will come at 11:06. Okay.
Okay, sir.
Hello, am I audible?
Yes, sir.
Okay. Okay. So my slide is visible to all.
Yes, sir, it's visible.
Okay. So next in the power dissipation is standby leakage reduction technique. Okay, so there is a lot of techniques that exist. I will discuss some techniques, that is power gating, VTC MOS, DT MOS, leakage feedback approach, and drain gating. Okay, so this is a powered gating technique, and sometimes we are also called this technique is MTC MOS, multiple threshold MOS technique. Okay, so what is in this technique? If you can see, there is a pull-up network and pull-down network, and two high gate transistors, high VT transistors, means the threshold voltage of these transistors are more. So these are called the sleep transistors. So we are using. So it is we are using between the first like this is VDD and between the pull-up network. So it is a PMOS sleep transistor, and this is your NMOS. Okay. Now suppose when it is in the ideal mode, like when this is not in operation, like when we are not providing any input, we are not giving any input here. So what will happen? What we are doing in this case, it will goes into the sleep mode. Means we are providing this transistor. This transistor will cut down in cutoff mode, and it will blocks the supply from VDD to ground. So it ultimately blocking the you can say the current from VDD to ground leakage. So because of this, when we are cut off mode, it ultimately block the leakage path from VDD to ground. Okay, so if the leakage is reduced, definitely there is a reduction in power dissipation, because what is the static? That is I leakage into VDD. And here basically in this is circuit level technique, basically we are reducing here I sub threshold. Okay, so this technique is a more effective technique and is also used in industries. Okay, the advantage in this technique, very high leakage saving and industry preferred. So multiple threshold, and these transistors are for normal VT. Okay, and these transistors for high VT. But what are the limitation in this technique? In active mode, propagation delay is more increasing due to series resistance of sleep transistors, because transistors are increases in series, and the TPHL and TPLH time will be more, because and high VT transistor definitely the delay is more. So delay will increase. Another challenge in this technique, like proper sizing of sleep transistor in a very large circuit, is very difficult task. Okay, and timing is critical for sleep signal generation. So we need to separately uh, need a controller who can generate, which can generate the sleep signals to these sleep transistors. Another thing, data retention problem. What is the data retention problem in this technique? Like in ideal mode, these are cut off, these are cut off. We are not providing, and then output here is floating. We don't know whether it is
Sir, your voice is not audible. You have muted your mic, sir.
Hello. Hello.
Yes,
My
sir.
voice audible? Okay.
Is
I think
audible, sir.
this portion. Okay. All of you listen this power getting or not? Because my this mic is unmuted, muted. I think this portion is not listened. Shall I explain this power getting?
Yes, sir.
Yes.
Oh, okay, okay. I'll explain it. Okay. See, this is the powering technique. Okay. So normally we also call this empty seam. Okay. And there is a technique. There is multiple. So the normal VT, normal volt, standard, and these are the high VT transistors. Okay. So why we using this high VT transistor? Because in high VT transistor, high threshold voltage leak. Okay, that's why. So in sleep, when when we are not giving any input, when you can say the circuit is not in your
Sir,
circuit
have you shared the
will
screen?
yes, I have shared the screen. It's
But
not visible.
yes, sir. Screen is not visible.
I have shared the screen, but why it's not coming? Once again, I'll share. Yes, I have shared. Check it's come or not.
Okay, sir. Yes, sir. Now it's coming.
Okay. Yes. So this is the in leakage power minimization. There is a first technique I am telling, that is a power gating or empty CMOS. What I am writing it is with my voice. So in this technique, there is a VDD and ground. Okay. So in sleep, these are the high VT transistor, and this is normal. Okay. So when this is not in operation, like we are not giving the input, this will enter in the sleep mode and this transistor cut off. Okay. And it will block the leakage from this VDD ground. Okay. Now, when in the normal operation, when the circuit is in operation, or you can say the normal operation, this transistor will be turned on, both the transistor will be turned, and when we are providing the input, based on the input, this circuit function. Okay, so the advantage in this technique is there is a very high leakage. Okay, inactive propagation delay increases in this circuit because we are using high VT transistors, and the proper size of the transistor is a challenging task in this technique, and timing is critical. So we need a one circuit that can generate proper signal, sleep signals. And another thing, there is a data retention problem because these are when we cut off this, so reach the data like when we cut off, so this node will be the floating. So again, this is data retention problem. Okay. Now another technique that is VTC MOS, so variable threshold MOS technique. So what we are doing in this technique, there is a separate substrate bias control, okay, and that is connected to the body, and it will separately control the body bias. Okay. So how it will control? How it will control? So what we do here, we provide VDD plus delta V and VSS minus delta V, and the threshold voltages of this transistor will raise. It will go to the high VT. The transistor will now convert into the high VT transistors. And because of this, as we know, the high VT transistor will reduce the leakage. So what we're doing by tuning the threshold voltages by separate controller circuit, we can able to tune the threshold voltages of the transistor, and we can able to minimize the leakage. Okay. Now another technique, that is DT-MOS. So dynamic threshold MOS technique. So what is in this technique? The body voltage varies with. So you can see in this technique, there is body. You can see the body is attached to the gate terminal. The body is also attached to the gate terminal. Okay. So based on the voltages, the threshold voltages will. Okay. So body voltage varies with the gate voltage. The ability of DT-MOS is dynamically tune the threshold voltages. So in this technique, what is the advantages? That we don't require any separate controller. Like in the previous technique, if you see the VTC MOS, we need a separate controller circuit, but there is no requirement because it is connected to the input. Okay. So when the circuit is in operation, like when it is in the operation, based on the voltages, it will forward body bias. Like this is on, it will forward body bias. It will work fast. And when it is not in operation, like this transistor, it will reach to the high VT in standby mode, and automatically reduce the leakage. So in active mode, body source junction is forward bias. In standby mode, it is reverse bias. So reverse bias means it will tune to high VT, and forward bias means it will tune to low VT. So low VT is good for delay, or good for delay reduction, and it is here reverse body bias is good for reducing the power. You can say the leakage power. But the limitation in this technique is this: the drawback of this device is that body resistance and body capacitance both increases, the result in higher RC time constant, which may shift the gate body signal level. So this is one drawback. Now another technique, that is leakage feedback approach. So leakage feedback approach is just what they are doing. This is data retention technique. So it is data retention technique. So what they are doing in this, suppose this is the circuit, they are placing one inverter here and it is connected to the two helper transistors. So this is here, this is helper, this is helper. So two sleep transistors and two helper transistors are there. Okay, so it will like the problem that we have faced in the empty CMOS, that problem we can solve here, like the floating problem. So like suppose when this is high suppose, and this will be the low, and low means here this transistor will turn on. Okay, so what will happen when it is in the sleep mode, like when it is in sleep mode, this will be cut off, this will be cut off, and we are not providing any signal. So suppose that is the 1 is there, earlier storage is 1 is here, and because of this there is a 0. So this will transistor will turn on, and this, because of this VDD will come here. So this node, the output node, not be a floating node. Okay, so it will reduce the data retention problem, the advantage, and minimize the leakage, because the sleep transistor advantages we will get. But you can say there is a penalty of the area, because we are adding the two more transistors, helper transistors, and so area and delay penalty due to additional transistors. Okay, so see how this will work. In sleep mode, this transistor will be off, this transistor will be off, and suppose the output is high here and this will be low, so this will be cut off, so this will be cut off, and it will reduce the leakage path. So leakage path is reduced even though this transistor is on, but see the bottom portion, this bottom portion is completely off. So it will block leakage path. Okay, is maintaining the data retention as well as blocking the leakage path. Okay, so this is the LFA technique. Now another technique is that drain gating. So drain gating technique, what they are doing, there is a pull up network and pull down network, and they introduce the sleep transistor between pull up and pull down network. Okay, so when this is not in operation, simply this transistor will cut off, this transistor will cut off and will block the leakage path. Okay, now the same like the disadvantage in this technique, like separate control is needed to control this, and due to standby mode, both sleep transistors are turned off and providing the stack effect. So probably these are in the series, so it is providing the stack effect, and when it is in the series we can able to reduce more leakage if we compare to the previous techniques. So it brings the stacking effect in this technique. So in this way we can able to minimize. So this is about the low power. One more portion I will discuss, that is the dynamic power. Okay, so I think this is clear to all. If anybody have a doubt in an low power, please ask. So I will start one more portion. Time is available, so that I will complete within the time.
Dear participants, if anybody regarding this session, you can ask.
Yes, anybody have doubt in low power? Okay, I will start dynamic logic. Okay. Okay, so dynamic CMOS logic. See, dynamic CMOS circuit we are also studying in digital IC design. There is one subject, digital IC design. Normally, MTech VLSI students are studying this subject, and it also we are studying this concept in low power because dynamic CMOS logic we also use for minimizing the power dissipation. Okay, so now we'll start the dynamic CMOS logic. So I think all of you have aware of static CMOS complementary logic. Okay, so all this we know. There is a two networks are there. There is a pull up network and pull down network, and simply there is a output and it is connected. So it is static CMOS complementary. All of you know, I think. Now, so what are the advantages in this technique? So very good current driving capability, high noise margin, and low static power dissipation in this technique. Okay, and the disadvantages in this technique is you can see the large number of transistor required. So because of large number of transistor required, it is required the larger chip area and delay will be more. Because if I have n number of inputs, so 2 to the power n times I require the transistors. Suppose if I have one input, then it will require PMOS and NMOS. If I have two transistors, so means 2 into 2. So total I require 4 transistors, means 2 PMOS and 2 NMOS. So this technique requires larger area. Okay, another thing, that is a short circuit power dissipation in this technique. Okay, so because there is a disadvantages in this technique, I need a technique which can resolve these disadvantages that we are facing in a static CMOS technique. So people are come out with some solution to solve these drawbacks. So we'll look at. So there is a one technique called pseudo NMOS. Okay, so what is in this technique? If you see the generalized structure, pseudo NMOS, it is like this. There is PMOS and there is pull down network, and this is a ground, and there is some inputs and there is some output. Okay, so this is pseudo NMOS. We are connected to this ground. This means it will be always on, and based on the input it will work. So suppose if you want to design an inverter, so just simply one transistor, and based on the input it will work. And suppose you want to design a NAND gate, simply NAND gate, what is this? I need 2 series transistors. So NAND like A dot B bar, so simply 2 series transistors are required here. But if I design with the same NAND gate, there will be total count of 4 transistors. Here you can see one pseudo NMOS and 2 series. Just I want to highlight. If I want to design NAND gate, using static CMOS, so simply I need 4 transistor, means A, B, so sorry, okay, and yes, so this is A, this is B, and final there is output. So total transistor here require 4. Okay, so means 2 PMOS and 2 NMOS. Okay, so this will give the functionality of A dot B bar. Okay, this is the NAND. So in static CMOS I need 4 transistors, but if you see here, here in this circuit, I am designing the same function A dot V bar using 3 transistors. So overall transistor minimized. If suppose I want to design a 3 input NAND. So total transistor I required in static CMOS 6, 3 for PMOS, 3 for NMOS. But if I design the with pseudo NMOS 3 input, so I required only 4. So 3 will be in the series in NMOS and 1 there. So total 4 transistor. So pseudo NMOS, what we are doing, I am minimizing the number of transistor. Okay. So pseudo NMOS, if there is an input, pseudo NMOS requires n plus 1, means n is this. Sorry. N is what? N is your number of inputs. So n is number of input. So it requires n plus 1. So 1 is what? But this. Or n is this. But if you want to design the same thing in the static CMOS, I required 2n. Okay. So if the suppose there is a 2 input circuit, so static CMOS, it will be 2 into n, 2 input, it will be 4. But in this case, it will be here 2 plus 1, 3. Similarly, if you go for like 3 input, simply 2 into 3, it will be 6 here, and here it will be 4. Okay, so this is the things.
Sir,
Yes.
while implementing the pseudo NOR gate in the VLSI laboratory, the output gets distorted, sir. But the pseudo NAND gate and pseudo NOR gate, we don't have any problem, sir. But in case of pseudo NOR gate, the output is distorted, sir. What is the problem, sir? I'm implementing the same circuit, sir. Pseudo NOR gate.
Pseudo NOR gate, yes, sometimes because that is always on. You check sometimes the width and length and dimension of that, and just check, just change the dimension. You check, and then check the outputs.
Yeah, I will check the WL ratio also, sir.
Okay.
Why we are
So,
getting that problem?
you check a different W by L.
Yeah.
Check with a different W by L, and then check the output.
How to identify what is the exact WL for that particular circuit, sir? Is there any method is there, sir?
Exactly cannot we can say, because when this type of problem arises, then we have to do the hit and trial.
Okay, okay, sir.
Yes.
Thank you, sir.
Sir, do we have any course related to current mirror circuit, sir, right now?
No,
Any lecture?
I am just teaching on the digital side. But that is the current mirror side, that is related to the analog.
And power optimization techniques, that also related to digital or analog, both, not sir?
Mostly, if you can say, the power minimization techniques are mostly we are doing for the digital type. Of course, there is analog, but mostly if you see the books, the techniques we are using mostly in the digital circuits minimization. There is a 2 books are there, Kaushik Roy and Ajit Pal. So you can refer, even with low power techniques we are using in SRAM and all these things. So all these are such digital type of circuits mostly. But of course, there you can do for analog also. Okay. So you can refer the books, Kaushik Roy book or Ajit Pal book. So you can see what are the techniques are there. And if you are doing in the analog VLSI design, then just check the circuits whether these techniques are applicable in my circuit, it can be fit or not. Then you can check. Now, if you see, so you can see in this technique, eraser is gone. Wait, just I'm sharing it again. And lower. Yes, screen is visible to all.
Yeah, yes, sir.
Okay. So if you see, there is a substantial reduction in the area, and the delay. Obvious, the delay will reduce because the less number of transistors, but static power dissipation will be there. Why it is there? Because this transistor is always on. So this transistor is always on, and it will get the leakage path is means the current is available here, and it will be easy from here. So there is a no block. Suppose when it is an off stage, then there will be more power dissipation. Okay. Now, if I do the comparison with static CMOS and pseudo NMOS, so static CMOS you can say the large area, pseudo NMOS small area, longer delay, smaller, and no static, there is a static. Why we am telling the no static here? Because if you see in the static CMOS, there is a complementary nature. Like if upper block is on, lower one is off. If pull up at network is on, then pull down network is off. So it's complementary nature. But here the one block is always the upper block, and because of this there is a static power dissipation in case of pseudo and MOS. Now there is another technique that is a dynamic CMOS. Okay, so this is I want to highlight, and you can see here in the dynamic CMOS what we are doing. We are using clocks. We are using clocks, and this is your pull down network. Okay, or you can say this is your there is a two types of operations going on. It will operate in two phases. One is pre-charge, another one is evaluation. Okay, so now when the suppose you are giving clock is equal to 0, means this transistor will on, this transistor will off. So you can say, so it will charge. So in this mode we call this is in pre-charge mode, because it will charging this the output load. Now when your clock is equal to 1, clock is equal to 1, so this transistor will on and this will be off. So this will be in evaluation mode. So this will be in evaluation mode. So based on the input, based on the inputs, it will simply discharge. Okay. So if the all the inputs are inputs get the path from output to this, so it will simply discharge the value. So if you want to design any logic, simply you have to change use the functionality in the PDN network. So this is the function. If you see, that is they have designed A dot B plus C bar. So this is your out. Okay. So simply if you want to design like a 2-input NAND gate, so suppose just A and B in the series and rest of the circuit will remain same. Okay. So and thus they explain like pre-charge phase what will be on and what will be off. Okay, and this. So so they have designed like if you see, so if you see for clock is so when clock is 0, the output node out is pre-charged to VDD by PMOS, and during that time the evaluation and MOS transistor M is off, so that a pull down path is disabled. Okay, and now in evaluation phase, like when clock is equal to 1, pre-charge transistor upper one is off and lower one is on, then output is conditionally discharged based on the input values. Down to if PN is off, the pre-charge is stored in the output capacitance CL, and the output it cannot be charged again till the next pre-charge. So notice the output can be in high mode. Pre-charge regardless of the input values and reading. Okay, so during the evaluation, clock is one conducting path is created out and A B is 2, otherwise it will remain in pre-charge. Okay, simply the out is equal to the clock bar AB plus. So that is, so one is clock bar means it is in pre-charge and this is in evaluation. Okay, so means what here? So when this is blocked, this part is completely this is cut off. So this part is totally blocked. They will not pass, and this will work. Okay. So if you see here, yes, so we'll see the advantages and disadvantages. So if you see the speed and power dissipation in dynamic, what you can see here, and now suppose there is 4 input. This is a 4 input NAND, you can say, and there is a clock. And sorry, what happened? Yes. So what happened here? When your this input and clock are low, means this is low and this is also low, you can say this will charge. But you notice at the end there is a sudden rise. There is a little rise, it's going up, and when there is changing, there is also a certain spike type of things will come. Why it is come? Actually, this is happens because of there is a capacitive coupling. There is a capacitive coupling. So because of this capacitive coupling, when this is changed at the changing end, there is a certain rise, and here is also in the changing end there is a certain rise. This will happen because of capacitive coupling. Okay, so the main advantages of dynamic logics are increased speed, reduced implementation area. So if you compare with the static CMOS, like if there is a 4 input I have designed NAND gate with dynamics. So total transistor count, if you see, there is a 6. But same type of circuit, if I design with static, it will be 8. So overall, you can say the area is reduced. So fewer device implement the logic function implements overload, capacitance is much smaller. Okay. Now, dynamic CMOS you can also design only PUN network, but you need to connect the output at this end now instead of this end. But normally in the books, if you see, they are mostly showing this structure. Okay. Now, what are the advantages in this technique? Dynamic CMOS, if you see the number of transistors required in the circuit, N is N plus 2. The 2 is what for? One is pre-charge, one is evaluation transistor, and N is the number of inputs. Okay, so but 2 in case of static CMOS. The load capacitance is more than 50% less than the static and is closer to the NMOS. So load capacity is overall reduced. And why it is closer to NMOS? Because only 2 extra transistors, that is pre-charge and evaluation, we are using. Speed of operation is fast. Obvious, it will be obvious because overall transistors are reduced. And lower static power dissipation, it consumes only dynamic. Why it is lower static? Because at one time, either this is on or this is on. So if this is on, this will be off. Okay. If this is on, so this will be off. So you can say the leakage path is not available from VDD to ground. So it overall reduces your leakage power dissipation. So lower static power. No short circuit power dissipation because the rising and fall, it's not taking much time. No glitching power because delay is not there. Okay, so it is a non-ratio type of logic, like non-ratio type, like if you whether you changing the WYL, it will not affect your functionality of the circuit. So sizing of the PMOS pre-charge device is not important for realizing proper functionality. So size of pre-charge device can be made large to improve low to high transition time. the trade-off with power dissipation, since a large pre-charge device directly increase the clock power. So all this thing. Now, what are the disadvantages in this technique? There is a disadvantage because nothing is one-sided. Charge leakage problem, sharing problem, or problem. So we'll see one by one. So what is the charge leakage problem? So this is your dynamic gate and depends upon the storage information in the form of charge. So during the pre-charge, this capacitor is charged. But the question is, how long it will remain? How long it will retain? And suppose the changing clock is too long. In that case, capacitor is discharged through NMOS network. It will not it can stand for a long time because of the charge leakage. Because of leakages, it will get the path from this. So suppose if you stored suppose 5-volt supply, according to the 5-volt you have charge. The node voltage is, suppose here is a 5-volt, and because of the leakages, it will get the path from there. It will reduce to 3 or 2. So logic 1 is not maintained. Okay. So another thing, you can, the output should ideally remain at the pre-charge. So ideally, when it is a VDD, ideally it should be 1. Okay. During the evaluation phase, this charge gradually leaks away due to the leakage current, eventually resulting in malfunctioning. So here you can see when your clock is low, it is pre-charge. It is pre-charge here, and suppose I am providing here A is equal to 0. A is equal to 0 means it is cut off. It is cut off here. Now, in evaluation phase, I am, suppose I provided 1. This is 1. This is also 1. So this will be cut off. This path is cut off. So my one value should remain 1 because in this is cut off. But what will happen because of this leakage? It cannot stand. It will start discharging, and when the next clock pulse come, pre-charge phase, again it will rise. So this discharging is you seeing, it is because of leakage. Okay. So same thing like within the transistor, because of reverse bias leakage and all these things, it will contribute. So I'm not going to go this. So simply this is, I already explained in the previous lecture, the reverse bias leakages and depends upon this. Okay. So what there is like this much amount, and leakage is one more thing, is dependent upon the temperature. So how we can compensate this? So if we can compensate this by refreshing at regular intervals. So like the concept we have used in the I think you have studied the dynamic RAM. Just we are refreshing because of leakages, there is charges down. So we need refreshing type of things at regular intervals to maintain the charge. Okay. So what is the solution here? Because the leakage problem is there, so high VT transistor and weak PMOS transistor we can use. So another thing, there is a charge sharing problem. So what is the charge sharing problem? Suppose this is a circuit and there is a capacitor. So at this end, if you see, there is a 3 input A, B, C, and suppose you are providing this 110. So 110 means 0 means here this is an NMOS transistor, this will be cut off, and there is intermediate node capacitance is attached at this node and this node. Now suppose you have stored some charge here and the level is 5 volt at the output level. But what is happens, it will take the path from this, and this capacitor starts charging, intermediate node capacitance. But what will happen to this at the 5 volt, the values get degraded. So this will get degraded, and sometimes it will reach to that value, it can be treated as logic 0. So it is, you can say it's a type of malfunctioning in the circuit. Okay, so the same thing, just I just have drawn the model for that. That is a CL, and 1 hour C3 is on cutoff. So these transistors are on. So redistribution of charges, you can say CL VDD and VL. So CL V into VDD and VA into this. Simply if you rearrange this, suppose the C1 C2 is equal to this much, if you put all these values, so our you can say because of the redistribution of charges, instead of VDD at the output, it will reduce by VDD by 2 because of a charge sharing problem. So I need a solution to solve this problem. Okay, how can overcome this charge leakage problem and charge sharing problem? Simply I will use weak PMOS transistor. What is in this? Suppose if it is weak PMOS, means there is a pseudo NMOS I have used here. So what will happen, suppose the one is charged here, so this is will be always on, this will be always on, and it will maintain the one value. Suppose if in case it is discharged, the one value is maintained by this weak pull-up, weak PMOS. Now the same disadvantage is like pseudo NMOS, there is always on, that then again will be there is a leakage problem from this to this. So what they have done, they just replace the output with the inverter. So if suppose if it is 1 here, it will be 0 and will turn on. So based on the output, it will turn on and it will maintain the one value. So if it is discharged by charge leakage or charge sharing problem, your data is degraded, high values degraded at the output, it can be maintained by this through this transistor. So same thing here, and you can say there is a bleeder of weak transistor, just they have attached with 2 input NAND gate. The same thing they have shown here. So we can overcome this problem by this technique. Okay. Now another thing, because of capacitive coupling, there is a like signal integrity issues will come. So now suppose this is the circuit and it is attached to another circuit in cascaded manner. Okay, and suppose there is A is equal to 0, B is equal to 0, and it is attached to this. Now when the clock is 0 here, and it is input is here. Okay, so because of you can see the capacitive coupling, there is again there is a rise here in there. So if suppose this is clock is equal to 0, means this will be 1. It means a high value here. High value here means it will turn on this transistor, and in case in this case now if the suppose is in first case if the input is 0, it will not get the path from this. It will not get the path from this. Now when you change this to 1, so when this input is turns to 1 here, the output to get discharged. This will turn on at 1, it will get the discharge path, but you can see the output does not discharge to ground fully. Why it is happen? This happens because of this capacitive coupling, because the charge that is loss of charge earlier because of capacitive coupling. So some charge is lost earlier, so that's why it will not reach to the ground. Okay, and now so now another thing, you see the output here is it comes to this stage. Why it is come to stage? See, when I am pre-charging mode, when my this should be 1, but because of this capacitive coupling, there is a loss of charge, and because of this loss of charge, the output value get degraded. And see here, there is a degradation in the out1 value. Okay. So there is a signal integrity issues will come if you arrange in the cascaded and sensitive to cost of effect. Okay, so this is all explained. And now another is cascading. Let's check how many slides are there. I will complete within the time. Yes, I will take some more time. I think within 10 to 15 minutes I will complete this portion. So cascading of dynamic gates. So suppose there is a dynamic gate and it is attached to this. So what will happen? Suppose in the first case when the clock is 0, okay, clock is 0, it will charge and it will turn on. Okay, so what will happen when the input is here is low and the clock is also low? So output, suppose it is a 1 is start, it will start. Okay, output is high initially. Okay, initially the input is high, and after some time when it's reached to high value here, it is this is also enters into this, the output get discharged. So there is actually some it will get discharged. Now we'll see at the out2 here. So when it is get discharged here, out1 is discharged here low value, so it will be in cutoff. So my output should not get path from this. My output should be, ideally it should be here, out2 should be here, but it's reached to this low value. Ideally my output should be 1, logic high, but why it is going down? It is going down because it will take the previous value, high value, because there is a finite delay of this gate. There is a delay in coming from this to this, and because of this it will goes down. So in the cascading nature, there is some signal integrity issues will come here. Okay. Now another, there is a clock skew problem. Like what is the clock skew problem? Like clock skew problem arises in dynamic CMOS circuit, particularly where whenever realizing multi-level circuit. Okay, so the clock is now distributing in the throughout the network, but depending on the clock network, it will reach at different points at different points of time. So this is actually the clock skew problem, and because of the different amount of delay of the clock tree network, there is a problems. So delay related to resistance and parasitic associated with the wire, it also resulted in hazard. So it actually bring the hazard or race condition in correct output. Okay. So how we can overcome this problem? We will see. We can overcome this problem. There is another technique called domino logic. So domino logic, just I kept one inverter at the output, and the problem like the cascading problem, like like suppose there is a one another is attached. So there is a one block is available, inverter is available, buffer is available. It will give some delay and directly it will not affect your cascading circuit. So the faulty discharge pre-charge nodes in CMOS can be solved by placing an inverter in series. Domino consists of two distinct components. The first component NMOS and second is a inverting buffer. So for example, during the pre-charge you are applying inverter, so when it is high, it will go low. So directly it will not affect. Suppose when it is high, it will not, because there is inverter buffer we have placed. Okay. So it cannot really discharge and it can realize the circuit, always get the correct output irrespective of the delay and clock skew problem. So this is the solution for that. And if there is a premature discharge during evaluation, it can also solve this problem. Okay. The introduction of static inverter has the additional advantage that fan out of the gate is driven by static inverter and low impedance, and with increases noise immunity, and the buffer furthermore reduces the capacitance. So advantages in this, the low power consumption, reduced chip area, that all we have, high speed, no short circuit, and another is no glitching power. So because of the glitching, there is a power dissipation that we can overcome. So what are the limitation is there? Because we have placed one inverter buffer, so always give in non-inverting nature, high switching activity with dynamic little bit more. Okay, so how to deal with this non-inverting property? So we can deal with like bubble shifting technique. So in bubble shifting technique, you can see this is an AND gate, and I can represent by De Morgan's like A bar plus B. So just I have to shift this bubble here and transform this gate to this. I can present in this form. Now suppose this is the circuit. This is the circuit. I change this one NAND gate to in this form. This bubble I brought here, this bubble I brought here, this bubble will be cancelled. Now this bubble I brought here, and now it transformed to this. Now this bubble is what? This is a inverter. So you can see this section, and this inverter is here. So now I can use domino here. Okay, so by transforming the circuit in another logic structure, we can use domino logic. But see, overall functionality should not change. So here the functionality of this circuit remains same. Only we have done some rearrangement to make suitable for domino logic. And simply dual logic, sometimes simultaneously we want like true value and complement value. So we can use this type of circuit there in domino logic. Now another technique, there is a NORA CMOS and NP domino logic. So what I am doing in this technique, there is just simply alternating NMOS logic, PMOS logic we are using. So suppose the output is here, now it is feed to the PMOS, and here we are getting some output. Now here the output is now feedback sending to the another block. So here you can see the clock we are providing, that's alternating clock, the phi and phi bar and phi, means when these blocks are pre-charging, so this will be in evaluation. Okay, so alternating way we can use, and this type of techniques are also used in industry. So compared to the domino technique, this approach is higher flexibility, and both inverted and non-inverted signals are available. And these techniques are also used in industries like alpha, DEC alpha processor, first 250 megahertz CMOS microprocessor. Okay, made extensive use of NORA logic. Okay, now we can see if I design the full adder with static CMOS, you can see there is a lot of transistor we are using. If we count the total transistor, there is a 3, 5, 5, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Around 28 transistor we are using in static CMOS. Okay, now same circuit, the full adder circuit, when you design with this, so total count if you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19. So total 20 transistors. So same function we are realizing with NORA CMOS using 20 transistor, and static CMOS there is a 28 transistor. This much total 8, there is a reduction of 8 transistor. So we can use also for minimizing the number of transistor, and in this way we can minimize the power. Okay, so this is all about dynamic CMOS logic. Is anybody have doubt, please ask.
For your participants, if you have any questions regarding these two sessions, you can ask.
Sir, what about the fast transistor logic, sir? Which one is more advantage than the dynamic CMOS logic, sir?
Fast transistor have some advantages like fast transistor but there is in fast transistor there is another issues like if you design with the NMOS type simply, so as we know the NMOS cannot pass good one.
Yeah, yes, sir.
So that is issues are there. So you can design with that, but there is a problem with that logic levels. So
Yeah,
if you compare with the past transistor and this, so this one is better. But past transistor types we are using in some circuits, like if you see the SRAM. So for transferring the some logic, like at you can say WS signals, at there we are using some.
So for example, if you want to implement a full adder circuit, sir, which model is more useful, sir? If you use a dynamic CMOS logic or static CMOS logic or fast transistor logic, which one is best suitable? How we will decide, sir?
See, if you want your correct outputs, like voltage levels should be good, and dynamic CMOS advantages, you know, the power dissipation advantages we have, like leakage power minimization, as well as delay point of view also good. But obvious, in past transistor there will be less number of transistors, so overall
Yeah.
area it will occupy less. I agree
So
with,
based
but
on our requirement, we will choose the method, sir.
yes, yes.
Yeah.
But I suggest better the technique is dynamic,
Okay.
because we can minimize the power of signal. There is no problem with the signal integrity. Okay, and another there is a delay problem we can solve. But the past transistor there is a problem of the logic levels.
Yeah.
So it may sometimes, if you fully design a bigger circuit, your some error type of output will come, a malfunction.
Okay.
Yes.
Yes, sir. Thank you, sir.
Any other
Thank
doubt?
you so much, sir.
Yes.
If anybody want to speak about the session, you can. Okay. Thank you so much, dear participants, and thank you so much, sir, for spending your valuable time and sharing your knowledge on low power relay design and dynamic CMOS design with us. Thank you so much for accepting our invitation and being a part of this 1 week STTP program.
Okay. Thank you all for listening my lecture. Okay. And if you have any doubts and queries, you can email me. Just writing my email address. So Rohit dot Lorenzo @ vitap.ac.in. So you can email to me. Okay. Please feel free and comfortable. Okay. Ma'am, can I leave now?
Yes, sir, you can leave, sir.
Okay. Thank you all.
Thank you so much, participants. You can leave.